My latest Raspberry Pi Pico project is a proximity warning sign, lighting up when someone approaches, changing colour if they get too close, using an RGB LED panel, ultrasonic sensor and some simple code. Ultimately, this will all be packaged up as a warning sign for my 3D printer, so small hands don't get too close to the hot surfaces, but equally could be used for numerous applications. If you follow my channel, some of this may seem familiar, and indeed it has a lot in common with my Mind Your Head sign, and I will be pinching some of the code and tech from that. But there's lots that's new, most notably my use of the Pico Proto board from MonkMakes, and in part this video is an introduction to that, and how with it and its breadboard sibling, it's easy to transition from prototype to production. So first of all, let's run through what we need, starting with a Raspberry Pi Pico, and I've got the one with headers, which I'm going to be using on the breadboard prototype. It is actually Wi-Fi equipped, but we don't really need that. Next up is an ultrasonic sensor to measure the distances, and mine is 3V compatible. For the illuminated sign, I've got an RGB LED panel, which we're going to program to change colour, depending on how close things are. Specific components are all listed in the description. For the prototyping phase, I'll be using a traditional breadboard, albeit one specially designed for the Pico, with all the pins labelled. Then when everything's up and running, I'm going to transfer my components to a Pico Proto PCB, where they'll be soldered for a more permanent solution, the pins clearly marked in the same way. Also for phase 2, I'm going to switch to a bog standard Pico, which at less than £4 is the cheapest in the range, and this will be soldered direct to the PCB. All the other connections will be made by jumper wires, but instead of flexi ones with plugged ends, I'll be using these semi-rigid ones from the Pi Hut. The variety of standard lengths being good for my breadboard and transferable to the PCB for a much neater layout. The final bit is my 3D printed front panel to house the sensor and the backlit sign. To get a better idea how this is all eventually going to work, let me run through my Tinkercad design. At the top is the PCB and Pico, my front panel at the bottom, facing downwards, and in between my components like the ultrasonic sensor, which slot into the recesses I've designed for them. The PCB being the other slice of the sandwich, with standoffs in between. The header pins of the component pushing through the holes in the PCB, where they can be soldered and trimmed to length. Exactly how this is going to work in practice will become clear later on, but for now it's a case of bearing in mind the final outcome when assembling the components on the prototyping breadboard and positioning the wires in between, ensuring we can make a direct copy from one board to the other. So now it's back to the real world, and it's just worth noting that in my CAD everything was upside down, and it's the front of the PCB we're going to work with, and for now the front of the breadboard, which has exactly the same layout, both with the pins conveniently labelled, so whatever we do with the breadboard can easily be transferred to the PCB later. So let's get cracking with the prototype by installing the Pico, pushing the headers into the holes at the top end of the board, evenly centred with the same number of columns on either side. I've actually used this particular Pico several times before, as with its soldered headers it's great for prototyping, before going on to the regular one. And most recently it was used on my Mind Your Head sign, so it already has MicroPython installed, and a couple of bits of code that's going to be useful for us later. Next we've got the ultrasonic distance sensor, and this one's 3V, so it keeps everything simple without any need for a voltage divider. And following my design it needs to go here, so eventually when the legs are straightened out, the two cylinders will fit through the holes in my 3D printed front panel, and any wiring I do here can be duplicated on the PCB. Now normally I'd use one of these flexible jumpers, connecting the positive of the sensor to the 3V output on the Pico, which is super easy to identify with the MonkMakes board. But that's obviously going to be much too messy when we come to the next stage, with wires all over the place. So let's bring in my Pi Hut jumper cable kit, which is going to make everything much neater. The wires are designed to bridge 2 or more holes in the breadboard, and are colour coded by length, so it's quite likely that we're going to end up with a mix of colours on any particular run. And I'm going to start with the positive for the ultrasonic sensor, using one of the brown ones to connect the 3V output to the positive rail that runs the length of the board. This in turn needs to connect to the VCC on the sensor, which we can do in 2 jumps, another short cable to row 21, and another to bridge the gap in the middle of the board. A pair of tweezers coming in handy to line it up and push the legs into the holes, flattening it down onto the board. And whilst a slightly more convoluted route than my direct wire, it's so much neater, particularly when we get to the soldered version. Now onto the other pins of the sensor, and if we were using standard jumpers, we'd probably plug them in over here, being easily accessible. but we want something a bit closer, and for that I'm going to need to take out the sensor temporarily. These are the 3 pins we need to connect: trigger and echo for the signal, and ground to complete the power circuit. And for the first of these I've got the shortest jumper, connecting row 22 to pin 15 for the trigger, which sends out the ultrasonic signal, which will bounce off any object and be detected by echo, the pin for which we're going to connect to GPIO 14 on the Pico with one of the grey jumpers, neatly sitting alongside the blue one. Finally, the negative ground, the pin on the sensor using row 24, and rather than overlapping the other 2, I'm going to jump over to the negative rail and back to the nearest ground pin on the Pico, neatly skirting the other 2 wires and keeping everything neat and tidy. Then back in with the sensor, all of its connections tucked away with no straggly cables. On the LED side of things, I'm going to keep it simple for now. We'll come to the RGB panel later on, but for testing I'm just going to use a regular one, plugging the legs into 2 vacant rows. And like the sensor, I'm going to use the outer rail of the breadboard, a grey jumper to pin 27, another to the nearest ground. Then for the positive, we're going to need a resistor, or the LED is just going to blow. The one I'm using is around about 200 ohms, plenty to protect the LED. And this will take place of what would be the positive jumper, running between the anode at 25 and pin 17 on the Pico, completing our wiring. To program the Pico, or in our case adapt the code already on it, we need to plug it into our host computer, and by opening a bit of software like Thonny, we can access any files it has, or save any new ones we write. As I mentioned, my Pico is the one I used in the Mind Your Head sign, and we'll be using one of those bits of code. You can see exactly how that was developed in that project video, and on my website you can find the finished code for this one, so I'll just scoot through it here. Essentially, it measures how long it takes for a pulse to reach an object and get back again, converts that to a distance, lighting the LED if that's less than 30 centimeters, which initially at least is pretty much what we wanted to do here, so we can use it largely as it is, just changing the input and output pins for trigger and echo to match our new wiring. Then, for purposes of testing, reduce our warning distance to a more convenient 5 centimeters. When the program runs, the measured distances appear in the shell, lighting the LED if they drop below 5, it going out again when they go further away. And program saved for now, let's get on with the RGB version. Its job done, we can take out the LED and the resistor, putting that to one side because we will need that again, and bring on our RGB flat panel LED. Now this looks quite different, but essentially it's the same as a regular one, just with the addition of an acrylic block, reflector dots on one side, clear on the other, which is the front of our panel. And like all RGB LEDs, it has 4 legs. The longest one is either a common cathode, or in our case, the anode, so I'm not going to need those wires to the ground. Instead, each of the cathodes will go to the pins on the Pico, so spreading out the legs a little, I'm pushing each one into a different row on the board. 30 will be the red, 29 the common anode, 28 and 27 green and blue. The ungainly angle of the panel obviously is temporary, but it will do for now while we wire it up. A jumper for the red going to pin 16, then a slightly shorter one for the green going to pin 17, skipping row 29, which is the common anode for each colour. It's slightly unfortunate that the colour coding is by length of wire, rather than the colours of the LED, but it's really no big deal, as with the labelling it's very easy to keep track. The last of our wires, for the blue, going to pin 18. Then it's back in with the resistor, connecting the common anode to the positive rail, already connected to the 3V output on the Pico. Wiring done, let's get it coded up, plugging it back into my host computer and saving a copy of the current code so we can adapt that for the RGB LED, the previous version safe in case we want to reference that another time. Now, instead of the single output for our white LED, we're going to need 3, one for each colour, starting with red at pin 16. Then rather than typing that out for each one, we can copy and paste twice, changing the first letters to G and B, and then the corresponding pin numbers to 17 and 18, as per the wiring on the circuit board. Then with each colour defined, we need to tell the program what to do with them. Once again, this is a case of adapting what we've already got, changing over to the new LED names, starting with red. But instead of a value of 0 being off and 1 being on, our logic is inverted, because it's actually the cathode that's connected to the pin, rather than the usual anode. So now 0 is on and 1 is off. And that's going to apply to each of the colours of our LED, which we can copy and paste, changing the letters just as before. So now when triggered by the distance, all 3 will come on, combining to give us a white light. And conversely, when all 3 have a value of 1, the panel will remain unlit. But rather than white, we want ours to be red, and rather counterintuitively, that means giving the others a value of 1, so they're in fact off, leaving only the red component to come on. And now when we run the program, we get just that, just a red light, actually considerably brighter in real life. And just in case you want to know what the back looks like, it is in fact quite a bit dimmer, even though it doesn't look like it here. So far so good, we have got an LED that lights up when something gets close. But now we want it to change colour, depending on how close. And the code for this isn't dissimilar to that triggered the buzzer in my Mind Your Head sign, which we still have on the Pico as Echo 2. And it's the structure of that we want to follow, adding it into our current program. First of all, let's increase our initial trigger distance when the LED lights. And then we want to add in a new bit, which we'll check again and see if anything has got even closer. Of course, it will only do this if the first threshold is passed, otherwise it will be skipped altogether. If the distance is now less than 5, we want a new set of colour values, so I've copied and pasted the ones from above. But to get them to apply only to the new distance, I need to indent them, typing in 4 spaces for each. And then we need to offer an alternative, which is basically to do nothing, and leave the colour values as they are, so I've pasted in another set, which we'll adjust accordingly. At the moment, both triggered colours are red, so I want to change my first one to green, turning off the red element with a 1 and green to on with a 0. And we want to do the same, to keep it green if things aren't nearer than 5 cm, only changing to red if they are. Running the new code also saves it, and we can see the distances in the shell, translating to my colour change. Green for less than 10 cm, red for less than 5. But green isn't much of a warning colour, so I want to do some colour mixing, and red and green together should give me a yellow. I could get a proper amber by using pulse width modulation, and I do have another video that covers just that. But for this one, I want to keep it simple, or at least that was the theory. In fact, rather bafflingly, it didn't work, and all I got was red changing into red. But after a bit of head scratching, I found a solution, which was to forget about the resistor, and put in a direct connection from the 3-volt supply to the anode, which seemed to work, giving me yellow and then red, with the bonus of a brighter screen, without, as it turns out, damaging the LED. I still don't really understand why the resistor would make a difference, but if anyone does have an explanation, please let me know in the comments. At this point I realised, admittedly rather late in the day, it would be better to ask my second question earlier, before setting my colour values, and getting rid of the first set would simplify the code, and make for a less jittery performance. Now even though it's working properly, my LED panel can't stay sticking up like that, but I've got a cunning plan, by which I can twist the orientation of the screen by bending the legs in such a way that they'll still be able to push directly into the breadboard without any other wiring. First of all, we need to carefully bend them downwards over a wooden skewer so the wire doesn't bend abruptly. Then continue bending so they start to wrap underneath the panel by different amounts for each leg. The cathode of the blue bending most, the one for the red bending least, until we've got a kind of fan, with the distance between the ends of the legs roughly the same as the spacing of the holes on the breadboard. Then it's a case of bending the ends of each one very carefully with my tweezers, so the tips are pointing straight down, with the elbows of the bend at roughly the same height, which means my common anode has quite a bit more below the bend than the others, it being the longest in the first place. Then we're going to reinsert into the breadboard, each leg in the same row as they were before, but along a diagonal rather than in a straight line, the bent ends of each one pushing straight down into the holes, the anode going quite a bit deeper than the other 3, the blue being the shortest and having bent the most, pushing in just enough to make the connection. I won't pretend this isn't quite tricky to get right, so you may need a couple of goes, straightening and rebending one or more, but with a bit of perseverance and a little bit of wiggling around to finalise the position, we've got a panel that's facing the right direction for our colour changing sign. Now for a bit more pin bending, this time on the ultrasonic sensor, as we want them to be pointing straight up, rather than at 90 degrees. They're rather more robust, so I'm using my long nose pliers, tip lined up with the elbow, so I can straighten them out without any kinks, also being careful not to bend them sideways. And even though this is a lot more straightforward than those of the LED, it's still worth being patient, bending them gradually with even pressure. The last thing we want is for them to snap. Even so, it doesn't take long to straighten them all out. But in the straightening I realise I've made a mistake earlier on, getting the orientation the wrong way round, and it has to go this way for it to fit in the front panel, which means my wiring for the legs is back to front, but relatively easy to rectify. The main thing is my positive and negative are the wrong way round, and I actually want row 24 to be for the VCC rather than 21 as before. so all I've got to do is move the existing jumper up the board so it'll connect to the right pin when I reinstall the sensor. Then removing the existing wire for the negative, I can pop in some new ones, connecting row 21, which still has that jumper across the middle of the board, to the negative rail that runs the length, connecting that in turn back to the ground, re-establishing both negative and positive on the sensor. The wires for the 2 signal pins can actually stay in the same place. I'll just swap over the numbers back in the code when I plug the Pico into the host computer again. 14 for trigger, 15 for echo, a pleasing coincidence that they're now all sequential. And running the code with our changes, we're back in business, very nearly ready to transfer everything over to the PCB version. But before we embark on that, one last task, which is to make our finished program the one that runs automatically when our Pico is powered up away from the host computer, by saving it as main.py, replacing the previous one. And that's the file we'll put on our new Pico when the time comes. So far this has been pretty much a standard Raspberry Pi Pico project. Components wired on the breadboard, running with some fairly simple code. Now we want to take it to the next level, moving everything over to the Proto PCB for the hardwired version. And for this I've got a second Pico, which I'll be soldering directly to the board, along with my LED panel and ultrasonic sensor, their positions having been planned in advance, along with the design of my 3D printed front panel, which has been gradually evolving behind the scenes, with the addition of a backplate to go behind the LED panel and hold it in place. Both parts mounted above the PCB using some standoffs, one for each corner, leaving space in the middle of the sandwich for the Pico, the components and all the wiring. And as the layout of my PCB is exactly the same as the breadboard, we can simply copy all of that. First up, my new Pico, a bog standard first generation one, onto the back of which I'm putting some double-sided tape so we can stick it on the front of the PCB. I could of course have used the one we've got already, pushing the headers through the holes and soldering on the back, but this is going to be much neater, and it will save my Wi-Fi capable one for another project, which would benefit from its higher specification. So instead we'll use the basic version, and with everything lined up and held in place with the tape, we can get on with soldering, making sure our surface is protected and we've got a nice clean tip. The trick here is to heat the pad on the PCB, feeding the solder in from the side so it flows in under the board. And even if, like me, you're no expert, it isn't that difficult to get a nice neat result, with just a little bit of solder rising up the castellation, so we know we've got a good connection. With 40 pins to do, this is a bit of a labour, but it really doesn't take that long, and pretty soon we're all the way at one side, ready to turn the board round and do the other. And before you know it, we're finished. All 40 are done. Of course, we could just solder the ones we're going to use, but doing them all is so much more satisfying. Pico soldered, we can get on with the rest of the wiring, removing the LED panel and sensor from the breadboard so we can see what we did in the prototype and copy that. Pushing the ends of a similar jumper through the equivalent holes on our new board, the labels making it easy to get them in the right place. Then bending back the ends of the wire just a little bit to stop it falling out. We can solder the pads on the back of the board, filling the hole in the middle around the wire so we know we've got a really good connection. One down, quite a few to go. That's the one that connects the ground to the outer rail. And now we want to do the positive one, connecting it to the 3V output on the Pico, just as we had on the breadboard. And we're going to methodically work through all of those wiring connections, replicating each one with a soldered wire of the same length and in the same holes, the labels making these easy to identify, checking back with the breadboard version, which is labelled in exactly the same way, so we know the wiring is the same and our circuit is going to work the same. With a bit of careful planning, none of my wires actually overlap, but even if they did, it wouldn't be a huge problem. They are insulated after all. And if our circuitry was that little bit more complicated, we could even put some of the wires on the back and solder on the front, a bit like a double-sided PCB, but far from necessary in our case. And here's our finished board, looking pretty neat and tidy, with all the wires in the same place as on the prototyping board, with spaces left for the legs of the LED, on the same rows as their wired connections, linking to the output pins on the Pico. To finish up, we can snip off the excess wire sticking out at the back, and at the same time check over our joints, making sure they're good and proper, adding a small blob of extra solder if required. All the wiring transferred, we're now into the final phase, and we can start by adding the standoffs to the front of the board. Like most of the other stuff, mine are from the Pi Hut, and once again listed in the description, along with prices. At 13mm, they're the perfect length, allowing room for all of our internal gubbins, yet close enough for the bent legs of our LED panel to reach from the front case to the PCB. Also in the description is a direct link to my website, where you can download the 3D printer files from my front panel, which sits on top of the standoffs. But before we fit that, we need to set up our brand new Pico by installing MicroPython, pressing down the boot cell button while plugging in the USB to our host computer. Other than the first steps, I won't go into any of the detail of that here, as I've got another video that covers the whole process. So if you are brand new to the Pico, give that a watch, as hopefully it gives the not-for-boffins version of the installation process. With firmware installed the next time we plug in the USB, we can access our Pico by using Thonny again. Obviously, as yet, we don't have any files, but I have made a copy of Echo 3 onto my desktop, which I can open in Thonny and then save a copy onto the new Pico, renaming it as main.py, so it'll automatically launch and run as soon as the Pico's powered up. All that done, it's now assembly time, as we no longer have to reach the boot cell button, and it's in with the ultrasonic sensor, lining up the 4 legs. And here's the final version of my front panel, into which the LED backlight fits, with room for the bent legs at the end. These in turn fit through the hole in my backplate, flexing them slightly to get them through, so they stick out the back just as before, and they'll fit in the same holes on the PCB as they did in the breadboard. Although lining them up is that much more difficult, with them trapped inside the sandwich, which won't close until we've got them in place, so a degree of patience is required, along with a steady hand. Being careful not to pop out the ones we've already done while lining up the others, but with a bit of gentle persuasion, each one can be guided into its hole, the final one for the blue requiring a bit of a prod with an Allen key. But when they're in, and our sandwich can close, securing them in place. Even the blue one, which only just sticks through its hole, won't be going anywhere all the time the case is shut. So with a final check to make sure everything's where it should be, let's get it bolted up. With the addition of the backplate, my front panel ended up thicker than planned, so I got myself some slightly longer bolts, and added some countersinks into my 3D print, which with the hex heads actually looks a little bit smarter than using the ones supplied with the standoffs, at least on the front. Then for one last time it's back out with the soldering kit, to make good the connection with the components, securing the 4 legs of the LED and those of the ultrasonic sensor, bridging the hole in the pad around each pin. Not only making the electrical connection, but also fixing the height of the sensor against the back of the enclosure. Then the same for the LED legs, carefully melting a small blob around each one, doing as tidy a job as possible, as our handiwork will be on show, even if it is at the back of the board. Then it's testing time to check all of our soldering and the software, which with a blink of white starts automatically as soon as we power up the Pico. And with everything working exactly as expected, we can go round with the final tidy, snipping off the ends of the LED legs very nearly level with the back of the board, although I've decided not to trim the ones on the sensor, as I think they look tidy enough anyway. Now it's time to add the messaging for my particular application, and I've designed something very simple, and hopefully easy to understand, printed onto overhead projection film, just using my inkjet printer. It's actually a double layer, laminated to increase the opacity. And now we want to get it inside, where it will sit on top of the LED panel, making our final backlit display. So it's out with the 2 bolts that were holding everything in place, and lifting the front panel ever so slightly, we can slip in my graphic, which is the same size as the LED, and replace the bolts, having successfully not disturbed anything underneath. And of course the display can say whatever you want, depending on your application. Mine could equally be used on a stove or hot iron, or even beside a sandwich toaster. And the message could be something completely different, protecting something fragile, or even warning of wet paint. But mine's for the 3D printer, and it's with that I've made a bracket, so I can mount my warning sign alongside. At the moment this is a bit of a prototype, and I'm attaching it with some sticky fixers onto that nice flat area on the back of the PCB. Eventually I'd like it to bolt to the back of the standoffs, but the sticky pads will do for now, strong enough to hold onto the bracket, which hangs from the side of the frame. Powering up immediately launches the program we copied over from our prototype, with all the parameters from the test version, and straight away we can see that we're going to have to change some of those distances, so our alerts are triggered from further away. And once again, connected to our host computer, we can edit our code through Thonny, changing the numbers for the trigger points. I also want to use this opportunity to make some refinements, adding in the briefest of pauses, to hopefully make the sign a little less twitchy. And as you can see, even though most of the time our Pico will just be connected to the power, it's easy to get in and amend the code to make any adjustments if required. And there we have it, Our responsive warning sign, functional and elegant, very much in keeping with the design aesthetic of our printer. Totting up the cost of all the bits, the whole project has come in under 30 quid, and over £10 of that is on stuff that we can use again. And for my next Pico project, I'll definitely be getting another one of those MonkMakes Proto PCBs.